So, welcome everyone. I'm really excited that you could be with us tonight. Tonight we have our friends at Sterile Ray. You all know John Neister. He's a familiar face around here now. And then we have Ed Neister himself, the guy behind the light, the guy who's opening up the world for us. So we're really excited to get to hear some more of the scientific, technical details about the light and let Ed sort of clarify for us some of those kinds of questions that we have. And then don't forget that we are also going to do some floor plan arrangements probably next week with John and Mike, where you guys can send us in your floor plans, and then we'll talk about placement of the sterile ray and where you can get the best advantage and avoid any of the shadowing or things that we've talked about before. So we are going to ask you guys to hold your questions until the end. I know we probably have quite a few questions from this group. So if you can save them up, and then we'll give you all an opportunity to ask the questions in the chat at the end. But meanwhile, welcome again, John, and welcome Ed to our group. We really appreciate you guys taking your time to be here and share your knowledge with us. And John, I will turn it over to you.
Okay. Well, thank you, Kara, and thank everybody for coming on a Friday night. You probably have a lot of other things you could be doing, but we certainly appreciate your time. Ed is a physicist. He started back in the 70s making lasers. He started with AFCO and then began his own laser company in New Hampshire, where he developed a new laser every year for about 16 years. He made lasers for NASA to track the sulfuric acid coming off their rockets. He made a laser for the Navy to track Russian subs 2 miles down, and he made the first tattoo removal laser. So he knows light, he knows skin, and in 1998, he was asked by the Dover wastewater treatment plant to come in and see why they weren't meeting their effluents. And he went in and saw these UVC mercury bulbs. And he said, why is everyone using 254? Is there another wavelength that might be better? So he went to UNH. He found a book back in 1935, and you'll see a curve in a few minutes. And it showed a higher peak absorption at 222, which we've dubbed far UV. So in 1998, he filed patents. Actually in 2005. Yeah. 2005, he filed patents for air, surface, and liquid disinfection. And in January of 2022, we got a patent for human skin, human tissue, and animal tissue. So he knows light, he knows the interaction of humans with light, and we've since had multiple studies that show this can disinfect both air and surfaces. So I'm going to share my screen and bring up a presentation and let Ed go at it. I can get this out of the way so I can play. There we go. Okay, Ed.
So, all right. Good afternoon or good evening, everyone. I'm going to go over the basics fairly quickly. I don't know everybody's background, and of course, you're not into the tissue interaction with light that I am. So I hope I try to simplify it, not to talk down, but to try to give you something that you can relate to, and give you some mental hooks that if you want to read and look over this PowerPoint that we'll send to Kara, you can have that as a reference, okay? I think let's start with the first basic thing is, what is a photon? And a photon can either be a wave or a particle. It's called the wave-particle duality. And when a photon hits a surface, it actually turns into a particle. It acts just like a particle. It transfers energy from the photon into the surface that it hits. And when it's in space, when it's traveling from the sun to the earth, it's in a waveform. It's just like electromagnetic radiation. It has a wave, it has a different wavelength depending on where it is in the spectrum. And so it's a very interesting tool that we have learned how to use to help battle bacteria and viruses. To give you a better understanding of what a wavelength is, if you look at the insert, you'll see the visible spectrum. And it has blue, green, yellow, and red. And those are at different wavelengths. In other words, the blue violet is about 400 nanometers, and the red and infrared starts at about 700 nanometers. So we have bands in the visible light that are called color. We also have bands in the ultraviolet light, and they are generally referred to as UVA, UVB, UVC. And that was all started back in the 60s to help the doctors understand the dose effect and the repercussions of getting exposed by these different bands of UV light. Since then, we've had UVC because it's germicidal. And now what we're promoting is far UV, which we would classify as UVF. And V stands for vacuum. And what that means is that wavelengths below 180 nanometers can only be used in the laboratory if you're working in a vacuum. That's because oxygen and water vapor absorb those wavelengths in less than a millimeter. So now you have an idea of going from the infrared to the X-ray, visible light, and ultraviolet. They're all different important features and bands of each one of these spectrums that make a difference in how they impact tissue and many other objects, especially solid materials. This is a far UV lamp. And you notice that what's unique about the lamp is that it has a different type of emission characteristic. It looks like little spiders, and that is generating photons. And how do you generate photons? Well, what we're doing is passing ions through a gas, and that gas is between two cylindrical tubes of fused silica with the vacuum first, and then we fill it with a special gas. And then we charge the surfaces of the fused silica, the quartz tube, with voltage, and we make ions in the gas space. That those ions impact the gas molecules. They accelerate those molecules to a higher energy state, and by Einstein's law of conservation, it has to drop back down to a ground state, and it makes a photon. So it's a fairly simple process once you understand the concept. What's very, very interesting is that we can use these photons to do work because each photon is carrying energy. As I mentioned, they're an energy carrier. This won't switch. Oh, okay. And because we can use that energy and we can figure out how to destroy various bacteria and viruses, then it becomes a very, very nice tool that we can put into practice. So now let's get into what a viron is and how does it disinfect? Well, you notice how somebody coughs or breathes, they actually eject bioaerosols. These are small air bubbles, if you will, that can go all the way down to 1/10 of a micron. Now, a micron is a millionth of a meter. So that's 1/10 of a millimeter. So it's pretty small. And when it gets that small, it's carried by the breeze in the air and the currents in the room. But you notice there's a big difference between a bioaerosol bubble that's 1 to 10 microns. They fall to the surface fairly quickly. But it's the small ones that are really bad for human exposure. And because when you have less than 20% relative humidity in the room, the 0.1 to 0.5 micron aerosols can float in the air for up to 8 hours. So that really increases your chance of inhaling those if you're in the room when somebody is sick. And one of the interesting things about the human body and the lung is that it has a mechanism that makes bioaerosols every time you exhale. A lot of people in the media world don't understand that, but as you breathe, you are exhaling viral particles. And that's only if you are sick and have a virus that's reached the stage where it's actually promoting itself through exhales. One of the fascinating things about this is that we have learned to use these bioaerosols to study the human body because those bioaerosols contain all the residuals that exist in the lung area. That's all the trash, if you will, that exists in the alveoli and in the lung system. And you can tell a lot about the human body by examining those. And that is the latest state of the art. So what does a virus look like? Well, a virus has a capsid that protects the nucleus of the core of the virus. And that capsid has those little prongs on it that you see. And those prongs are protein spikes. And how they infect is that they look for and attach to various cells in the lung that accept those. And once they attach, then the virus can take that cell and mutate it into something that becomes a workhorse for the virus to promote more viral particles. One of the interesting things about viruses is that they're very, very small. Their size is about 10 to 15 times larger than a water molecule. Can you believe that? I mean, they are small. And so what I've tried to do is to give you a graphic. If you consider a viral particle like the size of a baseball, that's a hard ball, and the 0.22 micron wavelength photon diameter is, when it hits a surface, is about like a soccer ball in comparison. So one impact with a photon from the 222 lamp, the far UV lamp, will totally engulf the viron. And because the energy of that photon is so much greater than the molecules dissociation energy, it actually ruptures the RNA that makes up that viron. And this gives you an idea.
I'm sorry, Ed, I don't want to interrupt you, but we've had a lot of talk about that. I don't know if you can go back to that slide.
Sure.
Can we clarify something? When you talk about the soccer ball versus the baseball, you're not talking about the actual particle size. You're talking about the amount of energy contained in that particle. Am I understanding you correctly?
Yes and no. Talking about the energy, you refer to that as 540 kilojoules per mole, which is the photon energy in that soccer ball. When you talk about the photon hitting a surface, it actually has a diameter, a particle diameter of 0.22 microns. And the viral particle has a diameter of 0.05 to 0.08 microns. So it's 3 to 4 times larger. The photon is 3 to 4 times larger than the viron. So it only takes one photon of 222 to impact a viron and totally destroy it. And that's what fits with the first law of photochemistry. If you have a photon and you have absorption, then you're going to get one effect by that photon being absorbed.
So the photon blows up when it hits a surface?
No, a photon doesn't blow up. The viral particle blows up.
I'm just trying to wrap my head around this because we've had a lot of questions about this. So a photon is a subatomic particle, right? And a viron is made of many molecules. So when we talk about size relative, it's sort of hard for us who are not physicists to wrap our mind around the fact that a subatomic particle is going to be larger than a multimolecular structure. So can you speak to that a little bit?
Sure. The photon isn't really classified as a subatomic particle.
Okay.
It's got a wavelength of 0.22 microns, which says that when it impacts a surface, that wavelength is the same size as the particle that is formed when it hits a surface and impacts it. So now you're talking 0.22 microns of size when a photon that's very, very tiny, but because of its wavelength, it only replicates a particle size equal to its wavelength, 0.22 microns, 0.22. It's not subatomic particle.
Okay.
It's got a wavelength characteristic and it's got a particle characteristic only on impact. Okay. Whereas your viron, the size of that viron is 0.05 to 0.08 microns. Okay, so that's 3 times smaller than the size of the 222 micron photon. And 0.08 microns is about 10 to 15 times larger than a water molecule. A water molecule is H2O. And that's 10 to 15 times smaller than a viron. So now you get an idea of the magnitude of subatomic particles. Yes, they are subatomic, but the viron's not subatomic either. It's a living biomolecule system. Okay, I hope that helps.
A little bit. I'm still going, okay, so it's floating through the air. It's not a particle, it's a wave. And so the length of the wave is then what determines the size of it once it impacts, if I understood you correctly.
That's correct.
So as it's going through the air, it doesn't have a diameter, it has a wavelength.
That's correct.
And then once it impacts, it gets a diameter because it basically assumes a particle form. So it's like a morphing thing, which is hard to sort of wrap our heads around.
Well, I can give you a better description. I was at Cape Canaveral when the second Saturn V lifted off, and we did some very, very interesting tests. And I can tell you for sure that I had a visual that confirmed that photons going through the air look just like a photon torpedo by Star Trek. So if you want to know what a photon looks like, go to Star Trek and watch a photon torpedo.
All right.
And I can confirm that, but I won't do that now. I'll do it at the end if somebody's interested.
All right.
It's an interesting story. Okay, we can continue.
Thank you so much.
You're welcome. So what we're looking at is a protein, and a protein has a very, very unique chromophore that's much stronger than amino acids. So a protein consists of amino acids, but it has some sulfur bonds on it, and it has what they call sugars on the tail end that turn it into a protein. What's critical of proteins is that they are the building blocks that give the viral particle the ability to take over a cell structure and take over the activity of the cell. So it's the proteins that are really critical to infection. And here is an example of the book that I found in 1935 that shows what they call peptide bonds, which are formed and make the proteins that peak at 200 nanometers, and the amino acids that peak at about 260 nanometers. And all the curves in the technical journals after about 260, 265 only showed the 260 nanometer curve. They dropped off the 200 nanometer because nobody made any lamps that produced light, and nobody knew any effects of the light in the wavelengths below 240 nanometers. This gives you an idea how peptides are made. You take your amino acids, you add some water, and you'll make a peptide bond. That bond is responsible for the chromophore that absorbs the light at around 200 nanometers, and 222, we direct that 222 wavelength to hit that chromophore. So we're going after the proteins by the peptide bonds that make up the bacteria, the virus, the capsid around the virus, the proteins there, and the lipid area, the lipid membrane that surrounds the COVID-19. That lipid membrane is all proteins. So it makes it very, very easy for a far UV to destroy the COVID-19 virus. This gives you an idea of the other concept of what a photon is. It's an energy bundle. It's carrying energy, and that energy is 540 kilojoules per mole. What's interesting is that if the energy that impacts a viral particle or a bacteria exceeds the bond energy, then it will cause that bond to rupture. So it's a chemical bond breaker. That's what far UV is. And if you look down, you see the sulfur bond has a kilojoule per mole of 498. That's less than 540. So yes, sterile array will break that bond, and you can see the critical biomolecules that are broken by sterile array on this chart. And I don't want to get too far or too deep, but a chromophore is a collection of molecules that make like a black hole in space. They form an antenna and absorb that particular wavelength. So if you look at the curve, it says n = 3, and see that arrow pointing to that peak. That says a wavelength of about 280 nanometers is going to have an effect on that biomolecule. But if we change the electron structure of the molecule structure and bring in other atoms, then we can get a biomolecule that has a replication of 4. In other words, 4 units, if you will. See how it shifts the wavelength? So that is what's really the key of how we make the far UV light really go after and destroy bacteria and viruses, is because we use this knowledge. What's interesting about what we physically do to a protein is like a slinky. This gives you a representation of that, and you can look at it. But I want to give you a visual. If you take a regular slinky, a metal slinky, and what 254 does, they talk about dimer formation. All that is like coloring different parts of the slinky with a magic marker. But what a photon far UV does is it actually cuts the slinky. It actually breaks the bond. So now you have part of the slinky falling away, and that molecule cannot recombine. It's physically separated. So that is the fundamental difference between far UV and 254 UVC. To give you an impression of what that means, if we do a single pass reduction kill in the air, look at what we see. UVC hardly made a difference. Far UV sterile array got 100%. So that gives you a visual of how important it is to have the right wavelength that has high photon energy and good size to break bonds. It's important that we do a chemical bond breaking, not just form dimers. One of the interesting things about disinfection is that we have several, we have the surface disinfection, and then we have air disinfection. So this deals with air disinfection, that deals with surface disinfection. What's critical is that surface disinfection, we need to know what the infectious dose is of the bacteria that's on the surface or the virus that's on the surface. So when we touch it with our hands and bring it to our face or mouth, can we get the disease? And to give you an idea of that, on the surface, the norovirus takes 10 viral particles, whereas MRSA takes about 400 to 500. So that's why the cruise lines need a log-3 reduction, is because generally high-touch surfaces have 5,000 CFUs or bacteria or viral particles on a high-touch surface. So if we got a 1 log reduction, we'd have 500 left. 2 log, we'd have 50. But 3 log, we'd only have 5, which is less than the infectivity level. So it's important to understand what we're trying to accomplish as far as getting the infectivity level below the infectious dose. And to do that, we also have to bring in time, which is the exposure of the light to the surface. With air, it's very, very different. And the reason why is that in air, the bacteria and the viruses are basically not clumped together. They are free to move around. In some cases, they'll clump, but they don't clump nearly as much as they do on a surface. So if you have fewer bacteria to be exposed by the light, then it takes just a few photons to break that bond and to kill that particular bacteria. Whereas on the surface, if you have a pile of bacteria on top of each other, you got to bore through all the bacteria on the top to get the last ones on the bottom. And that's why it takes so much energy to get the surface versus why it takes one photon and one impact will take care of the air. One of the interesting things about the efficiency in the air is if you look at the 3 different charts there, you have the small a, and then you have a medium A, and you have the big A. And what that means is that as the photons move from the lamp to a distance, they're traveling at a foot per nanosecond. So it takes 1 microsecond for a photon to go 1,000 feet. It's going to go that 1,000 feet if it doesn't hit anything. And it's not going to hit molecules, but it is going to hit viruses. And it's going to hit any bacteria. So the critical part is for air, we really look at a probability for how long it's going to take to destroy those viral particles or bacteria in the room. So if we have one person infective and shedding a virus, they may be producing 200 to 1,000 viral particles per exhale. That's 15 times a minute. So in 1 minute, you could have 1,000 times 15 or 15,000 viral particles floating around. So what is interesting is if you look at the chart, the 3 different curves, is that if we're real close to the lamp, the probability of impact is pretty great because you got all the photons hitting a very, very small area. But if you go further and further away, the photons are spread out just because they're going in a straight line. Don't forget, light doesn't change direction. It goes the same way all the way until it hits something. So now the photons are spread out, but they're random. So now the question is, what is the probability for us to hit a viral particle moving at 1 foot per second at 100 feet? Well, we're going to ask a probability specialist that question and get an answer. But the key is that if we have the lamp in such a way that anybody that exhales air, that the light hits any air coming out of the person's mouth before it can go a foot, then there's guaranteed that it will kill any viral particles and bacteria before it's inhaled by a person another 2 feet away. So that is really the cool thing, because most air velocities inside a room are about a foot per second. So that means that if you exhale, we have about a second to kill that. Well, if you look at a dust particle in the sunshine coming through the window with a good background, you'll see bright particles. But you don't see those particles flickering if they're in the light because there's so many photons hitting it. And that's what far UV light does. It produces 10 to the 15th photons per second at 5 millijoules. So if you have 10 millijoules, you got twice as many. If you have 100 millijoules, you got 10 times to 20 times more photons. The key is that we're making so many photons that the probability is very, very high that we're going to hit viral particles and bacteria before they can become infectious. And I've got some personal stories to tell where I've been involved with lamps in my area, and I had 2 people that were shedding the COVID virus, and nobody else in the family got it. So we've got a lot of different stories of how effective this really is. This gives you just some representation that I wanted to include so you can take a look at it for those that are interested on how the light expands from a point source and why it approaches 1 over r squared. A lot of people talk about 1 over r squared as the intensity as it moves away from the lamp. That only refers to a point source. And what's really important is that we don't make a point source. We make a lamp that can be as much as 2 feet in diameter. So we have a lot more photons coming out from our lamp than we can possibly have from a point source. I wanted to get into just briefly the safety aspects of far UV. You will see the UVA region, which is your tanning booths type, and the 365, which is used for psoriasis. You use the UVB region, which is not really used too much. There is some tanning booths in that lower wavelength. But you see how the adaptability of the human skin is for UVA and UVB. One of the interesting things is recently they found that some of the drugs are affected by UVA, and that tends to create melanomas. So they're being very, very cautious about recommending exposure to UVA as opposed to 20 years ago. The UVC is germicidal, and we've always known that it penetrates very deep into the skin. And UVC will penetrate fairly deep. It'll go down into the dermal area, which is the active skin region, which is live tissue. And one of the interesting things is that it will cause what they call erythema. So when you are in the sunshine and you get 280, 290 right there at the seacoast at 0 sea level, you're going to get erythema in about 10 to 15 minutes on a real hot day. And that's because the photons are penetrating into the active skin dermal area. Far UV does not penetrate past the epidermis. And you can see that you get into the far UV region, the safety goes sky high. And those numbers were done quite a while ago, very, very conservative. But at 220, we put 5,000 millijoules on the skin and not created any damage, any erythema. And we think that the threshold limit values today are still very, very conservative. So we don't see any downside to using far UV. We have been doing tests on safety for eyes. We've been able to kill the amoeba parasite, acanthamoeba parasite in the eyes in about 15 seconds. And we've tested corneas and shown that we can go over a minute before any indication of damage occurs. And that's with the lamp within a centimeter of the eyeball. So this gives you a better technical reason of why this is so interesting. That 222, because of its short wavelength, doesn't penetrate cells, but it does get into the bacteria and particularly the viruses. That's just for your own information for the future. One of the fascinating things about 222 is that it's made in an excimer lamp. But what's interesting is from all my studies in 1999 and 2000 and beyond, until I filed the patents in 2005, showed that there are 21 factors that control the emission and the performance of an excimer lamp. In other words, you can have a Ferrari and an excimer lamp, or you can have a Volkswagen and an excimer lamp, and they are not the same, even though they make the same wavelength. Their spectral content is different, their lifetime is different. But what's really interesting is that in the development, I found that we could make 257 because the one particular gas additive in the lamp is combining two of those same molecules and producing 257. Well, 257 can be dangerous if the exposure is very high. But our lamps do not produce a very high exposure at 257. So therefore, we don't need a filter at all. Whereas all the other lamps that we've seen produce a lot of light at 257. And I like to compare it to a 100-watt light bulb versus a night light. Our lamps produce almost 90 times less at 257. So that means that if you had a 100-watt light bulb, you might get 1 watt of power, light power, out of that lamp. And if you look at the difference in a room and you have a 1-watt night light, you can barely see that, but you turn on the light bulb and you're going to see that in pretty good shape. That shows you the difference between that. Whereas the lamps that require the filter are only 14 times down. So they're in the order of 8 to 10 watts, about 10 times more emission at 257. So in the course of a day, you can start to exceed the threshold limit value at 257 nanometers. And that's why many of the companies in China and Japan have to use the filters, because their design of their lamp, the way they make the lamp, and all the other factors that involve the performance of the lamp, they do not understand how it controls that other wavelength 257. Whereas stereo lamps do not produce hardly any light at all, almost 100 times down at 257. So you never have to worry about having a filter. Okay, any questions? I've got a lot of extra slides depending on what questions, so we can get into it.
Okay. I'm glad you touched on that, because the other kind of lamps that you're talking about who have the filters, aren't they also LEDs? They're not tube lamps, right?
No, that's not. They do have companies that are making LEDs. Yes, they do, but they do not make 222 very efficiently. So you're not going to see too many LEDs in commercial practice just because they're inefficient. LEDs are good for visible, and then they get a little bit less as you get into the UVB and UVA area. And when you get down to close to UVC, the limit right now is about 260 nanometers. They can't go below that just because the metals absorb short wavelengths. So it's very, very difficult to make a conductive surface like an LED and not have it absorb the wavelength it's producing. So that's a real tough thing for LEDs to do. They're not going to be efficient in the UV. So the lamps that you're seeing from China and from Japan, they're all excimer lamps, but they're very, very small. And because of their size, they have a physical limitation, and they'll never be able to get rid of 257. That's one of the drawbacks of having a very small lamp, is that physically it's going to be very difficult to do that.
Okay, because that's one of the biggest questions that we do get is, how do you know you're only making that 222 nanometer wavelength? But you're saying you're not. You are making some 257, just not enough for it to be an issue.
Yeah, it's like 1 watt night light compared to a 100-watt light bulb. That's basically what it is. And that's all from the study that we had the University in New York do an extensive test. And those are the numbers that they came back with that showed that we're hardly making any 257.
And then you talked a little bit about you double the distance, you quarter the strength of the light, or I'm not using the science technical terms, the radiance or the intensity or whatever it is. The question that's on everybody's mind too is the distance. You say you've got about a second to kill the virus. How far away can you be and the light still kill the virus in a second with a sterile ray unit?
Yeah, I think the biggest impression that you should have is that you don't want somebody to be in the shadow so that no light's hitting the area. if light is hitting the area, it'll travel 1,000 foot in 1 microsecond. Okay, so we live in spaces that are less than 1,000 feet. So 1 microsecond is a millionth of a second. So we're going to get the virus as soon as it gets into the light path from the lamp, direct line of sight. As soon as it gets into the light path, it's dead. And why we suggest that you have a lamp facing one direction and one across from that is to get rid of the shadows. So you don't have a shadow, you have perpendicular exposure, and now you don't have, you minimize the shading.
Yeah, we've talked a lot about shadows and shading. I think that's pretty clear. What the question is how far away from that sterile ray, if you've got your 150 watt unit, you've got your saber there, how far away can you be to still keep enough power to kill a virus in a second?
Well, you have enough power. The fact of the matter is you're throwing out like 10 to the 16 photons per second. So if photon hits a viral particle 1,000 feet away, it's going to kill it. The problem is that if you stop the photon from hitting the viral particle, then you're not going to kill it. So it becomes a probability when it's in the light region. But recognize that I have, let's go back to this one slide that I had, and let me just give you an example. Let's say that the middle shield there, the middle A, is a 10-foot high wall that's 20 feet left to right, and it's 10 feet in front of the lamp. I calculated that there are 10 to the 15th 0.1 micron spots on that wall. So if I'm producing 10 to the 15 photons per second, what's the probability of me hitting every spot on that wall? Well, it's almost like you're throwing paint at it, and after a while, it's all black. So now the question is, what is the probability? Well, I can almost guarantee you that you're going to hit every spot within a second, because you got 10 to the 15 photons and you got 10 to the 15th spots. So now the question is, how far out can you go when it's going to take a second? It may be 50 feet or 100 feet or 200 feet. We're going to get a probability expert. That's not my specialty. We're going to get a probability guy to say, okay, it's going to take 1 second if you're 550 feet away to get all the bacteria or all the viral particles at 500 feet. And I think of it a different way, Kara. I think of it as if I had one person exhaling a viral particles and he was 100 feet away, then how long would I have to wait for that air to get to me before I know that it's dead? There's nothing alive in that air. And I would say, okay, if it's 1 foot per second, if it goes 3 feet, am I going to get everything? If it's in the line of sight, I'm pretty certain it is. But we're going to find out when we get the probability guy to give us some numbers. But I would say, I'm always looking at 500 feet or 1,000 feet because that's 1 microsecond, and that's nothing in time. I mean, every microsecond, that's a millionth of a second. So you've got 1 million times 10 to the 15 photons per second going
per centimeter. Per centimeter.
Yeah.
Yeah. So basically, for those of us who have living rooms, right? Like most of our living rooms are not going to be 500 feet, right? they're going to be, maybe 20 feet by 30 feet or something like that, right? So I'm hearing that you're real confident about the density at 10 feet, right? Like the probability that you're going to hit. I'm hearing that sort of beyond 10 feet, then the probability we haven't really figured yet, but you're getting somebody to figure that. Is that what I'm hearing, or?
Yeah, we're getting somebody to figure that, but recognize that if I go 20 feet, then I still have maybe twice to 4 times more 0.1 micron spots on that wall, just going by the square of that distance. So if I got 4 times more spots, then is it going to take me 4 times instant, 4 times 1 microsecond to get them all? You see what I'm getting at? The 1 microsecond is so fast that if I multiply it by 4 times, I've got 4 microseconds. Okay.
So what you're saying is, I'm trying to wrap, as a more of a lay person when it comes to this subject, I'm trying to wrap my head around it. What you're saying is, when you're telling me you're splattering the paint against that second wall, you're not just splattering the paint one time, though. You're like continually doing it because your light is continually emitting those photons. So at 10 feet, you're pretty much like black really quickly. And at 20 feet, you're still pretty confident that you're black before that second that it would take for the virus to get to you and you inhale it. So the question is, how we have that 1 second time factor as I'm splattering much faster than a second. So the question is, like at 30 feet, am I still splattering fast enough to paint the wall black in less than a second?
Yeah, I think if you go another 4 times, so you're talking 16 times, now I've got 16 times more exposure, but I'm still throwing the paint at 1,000,000 times a second. So
the viral density, I mean, I guess the viral density has a little bit to do with it. Like if you're in a very dense viral vapor cloud, but you're talking about basically creating walls of photons, it doesn't really matter if you have 5 virons hitting it or 500 virons hitting it. If you're making an oblique space, you're stopping them.
That's correct.
Yeah, think of it as a car wash of photons. You're literally in a fire hose of photons. And it's not 10 to the 15th photons per second. It's every centimeter of that lamp is making 10 to the 15th photons. So we have 10 inches of lamp in the 150 watt saber.
That makes
sense. Let me give you an example of that is a visual. If I measure the intensity or the effluence from the sun in Somersworth, New Hampshire, then I can get on a hot day 1/10 of a watt per square centimeter. Okay. Now I can go to California that same day and make the same measurement, the exact same measurement. Why? Because I'm far enough from the sun that it acts like a point source. So if I have a big lamp and I'm producing 100 watts, then all that power is going out. If I have a small lamp and it's only producing 1 watt, I can see that with my eye when I walk into the bedroom before I turn the light on. I can see a very little glow and I turn on the light and boom, it's all bright. That is the difference between a coaxial lamp made by Cheryl Ray and these little small lamps, is we're delivering a lot more photons than a small lamp can possibly deliver. And you can see that with your eye. Your eye's a very good detector. You see a 100 watt light bulb, it's a lot brighter than a 1 watt night light.
Yeah, I think it's starting to gel in my head. I'm going to read you some questions from the chat.
Okay.
So the first question says, so say someone has COVID and they're 15 feet away from the saber. If I'm understanding correctly, it's 1 second for it to kill the COVID particles, or am I misunderstanding?
You're misunderstanding. The reason I use 1 second is air moves a foot per second indoors. So all I'm saying is that we have at least 1 second for those photons to kill anything in the air. Is that easy? At 10 to the 15, 10 to the 16 photons per second at 10 feet or 20 feet or 500 feet. Yeah, it's real easy.
So El, he's not saying it takes 1 second for the light to kill them. He's saying that you have 1 second till you breathe them in. So he's got to kill them faster than 1 second because he wants to kill them before you breathe them in. And he's saying that 1 second is actually a really long time based on how much light and how fast the light is coming out and how much light there is.
Yeah, and the reason I use 1 second is that normally in a crowded room, people are 3 feet from each other at a minimum. And if you go 1 second, the air can only move 1/3 of the way to the next person. It has to reach the next person before they can inhale it. So 1 second is a pretty safe number compared to 3 seconds that it takes on a normal airflow movement indoors to get to the other person to make them infected.
Well, that's why we like to be upwind of people that are infected and not downwind, because if they have a little push, then it gets to us faster, right? So, and that's some of the arguments about air filters in classrooms sort of are built around this principle about who gets the viral, particle pushed to them faster and those kind of things. But if you're talking about 1 foot of movement per second, and you're talking about being several feet apart, then yeah, if you got a continual, like John says, car wash of photons, then you've got a lot of time on your side there.
You got that. And one of the interesting things, the National Institute of Health came out and said the best way to handle school classrooms is to have all the hot air coming in at the floor and going up out of the ceiling. In other words, make them like a fume hood. And they're absolutely right, because it's going to carry all the viral microorganisms out of the headspace and get it away from people from being able to inhale from other people.
Well, and if you think about it too, we have some air filters that suck the air into the sides and they blow it up out the top. And we have other air filters that are blowing, sucking it in one side and blowing it out the other. So if we're trying to avoid pushing the air towards us, we should be using more of the models that blow the air up and versus the models that are blowing the air sideways.
That's correct.
That makes sense. All right, our next question is ozone emitted?
We make a little ozone, but it's, how do I explain that? Ozone is a way of making O3 from oxygen, but it takes time and it takes a changeover of the air. In other words, you can't have air sitting still and be able to measure the ozone. We make it at somewhere in the 6 to 8 parts per billion, but that is effectively no ozone. And the only way we can measure the ozone is to have almost still air, hardly move the air at all. Because the faster you move the air, the less the ozone is in the air, because you have more oxygen compared to ozone. So we don't consider that an issue because we are making a system to send to the UL to get 0 ozone certification. And we think that that'll be a marker for the industry that will set us apart from everybody else. And we have a unit that's just about ready to go to get tested to meet the 0 ozone standard. One of the things that everybody should remember is that just about any device that uses electricity can make ozone. We know for a fact that the laser printers are making about 40, and I don't want to confuse you, but they're micrograms per liter of ozone per copy cycle. And nobody has even thought about that or discussed that, but they have because of the lamps and because people feel that all UV makes ozone, and that's not the case. I've actually demonstrated to a major air conditioning company that we can actually reduce indoor ozone. And we can drop indoor ozone down by 10 parts per billion very, very easily.
All right, and then Kyle has a question that says, what are the most recent tests, research, and data that Sterile Ray has done for these products that's publicly available to educate ourselves and the public wanting to understand how far UV can help them? And before you answer that, Ed, I'm going to say, Kyle, part of your question is my fault. John has sent me a lot of like the study data and stuff that I still haven't made the compilation and posted in our files. So anything, John, that you have sent me, I will compile and put in a file in our groups. I just haven't gotten around to that. But is there other publicly available data that you have that you haven't sent me, or do I have it all?
You have most of what we've done, but now, thanks to our infringers, there's plenty of studies all over the world.
Thanks to our infringers, I love that.
And I'm not saying, I mean, there's a lot of professors, there's a lot of indoor air quality experts that are looking at far UV and doing some great research that we just literally can't afford. But we do have several studies going right now that I can't talk about, but they'll be coming out probably in the next 2 months or so.
Okay, great. So Kyle, you can feel free to poke me and nudge me to get the studies and stuff that John has sent up in our group, because some of that is me being behind on posting things.
Right.
I put something up that may help people understand my comment on the 20% relative humidity, and it's extremely important that nursing homes and homes that have elderly in care have their relative humidity up as close to 50% as they can during the winter. And the reason that they don't, it has a direct impact to the number of people that get COVID in their facility. And this just gives you a report that went through and did a very, very detailed study on how relative humidity controls the airtime that the virus can stay, so that it's potentially inhalable, if you will, by people in the room.
So along with a lot of us, we have our carbon dioxide meters that we're using to make sure that our ventilation is adequate. Some of them actually come, or I think it's even cheaper just to get a relative humidity. We should be also in our living spaces looking and trying to make sure that we're hitting that 50% relative humidity if we're interested in optimizing our chances of not transmitting things.
Yeah, I think it's hard to get the 50% humidity in indoors during the winter here in New England and in the upper Midwest. But if anything you can do to keep water in the air, it will dramatically reduce the fly time of these bioaerosols. Now, this is talking about bioaerosols in the 1 micron and the higher. But when you get into the 0.1 and 0.05 micron air bubbles, the fly time is out to 8 to 10 hours. So this is just one study. There are many studies if people are interested. You can just Google it.
Right. Great. Okay. So our questions have slowed down in the chat. Does anyone want to orally ask a question? Do you guys have any more questions right now? Or do we want to let Ed move through a few more of his extra slides? I'm going to see if I can see more people right now.
Well, while you're doing that, Carol, I'll just talk to you about how I visually compare the photon movement in space to a photon torpedo by Star Trek.
Yes, that would be great.
I had a group that bought a laser. I've been in the laser business for over 20 years, and I made tunable dye lasers so we could change the wavelength to fit the target, just like we're doing with 222. We use the 222 nanometer to target bacteria and virus, DNA, and RNA. We had this group bought a laser, and they were looking at, for EPA reasons, looking at smokestacks to discern what the nitrogen oxide and sulfur dioxide contents were coming out of the stacks. And the EPA, NASA hired them to go down after the first Saturn V rocket took off. The solid state boosters mixing with the water created sulfuric acid and a hydrochloric acid, in a high concentration. And what was interesting to the story is that a farmer walked into NASA right there at Cape Canaveral 2 days after the Saturn I launched and said, "You need to buy me a new tractor." And they said, "What?" And he showed them a picture. It was a brand new tractor. And 2 days after the launch, it was nothing but a bucket of bolts. And so NASA said, we got to plot where these clouds are going after the Saturn takes off. So they hired this group that had the laser that I made, and we went down to Cape Canaveral, and I was asked to be there just to make sure everything was working fine. And we were 4 miles from the Saturn II launch, and I don't remember, I think it was the Gantry B, which was 4 miles away. And we had the system, it was all computer controlled. The laser fired at 10 pulses per second, and the pulse width is 300 nanoseconds of the pulse. Now, in a laboratory of 30 feet, the light looks continuous when it hits the wall. It goes from the laser to the wall, it's 30 feet, but the pulse is only 300 feet. But you couldn't discern that. So anyway, we're doing 4 miles to the gantry, and the night before the liftoff, we're doing test shots and firing a laser at the gantry A, which is 4 miles away, just to calibrate the computer. And we're firing this laser at 10 pulses a second, and it was the prettiest thing I'd ever seen in my life. You get these bolts of lightning, bolts of red light going through space, and you can literally see multiple ones going out and hitting the gantry. And every time a pulse hit the gantry, it would burst into brightness. It was really, really cool. So I said, all right, that's a photon torpedo, guys.
Hope you got some pictures.
We're going somewhere.
All right, we got another question here, a couple questions. I was wondering about maximum exposure times, as in how long can you be under the lamps a day? We have some up doing to necessary house repairs, and we're sitting under them a lot.
Yeah, I think that the best answer to that is twofold. Number one is that I found that I can use 222 to kill the foot toe virus. Mold. Yeah, I'll be all right. Fungus. And I put as much as 5,000 millijoules or 5 joules on my foot, and no erythema. There was nothing that odd occurred. I did kill the virus. I mean the fungus. And to prove the point, about a month later, the toenail off the big toe just came right off. I mean, I killed all the fungus underneath the toenail. I got the fungus when I was playing basketball in high school, so I've had it for a while. But the interesting thing also is the dose and the time.
So are you saying if we put our feet under the lights, our toenails are going to fall off?
No. I'm saying you're going to kill the fungus if it's underneath the toenail.
I'm teasing you, but you know someone will edit it and say that. So not really.
Anyway, the interesting thing about the exposure is that it's all relegated to what we know about sunlight, and that is the threshold limit value is for a certain dose over 24 hours. And we know for a fact, because of all the studies with sunlight, that you can get a certain dose of sun every 8 hours for each 24 hours and not cause any serious damage to your skin. But if you exceed a certain number for every 8 hours for 24-hour period, that's when you start doing damage. So, and it goes as a strange number. If I have 100 millijoules exposure allowed for 8 hours, then if I'm only under that light for 4 hours, I can have 200 millijoule exposure. And if I'm under the light for only 1 hour, I can have 400 millijoules exposure. So when I did 5,000 millijoules in 5 minutes, then there was it fit the reciprocity numbers fine. So it comes down to the dose and the time that you have to be concerned about. One of the other aspects is that if you're in the room, and this was a study done by Harvard University, they showed that the average person in the room with far UV in the light only gets about a 30% dose compared to the maximum they could possibly get if they sat still. So
okay, let's just assume that I'm in a room and I'm 10 foot from the light and I'm sitting still. How long can I sit under that light?
Yep.
We measured the saber, and at 8 hours, you're only accumulating, if you were sit there 10 feet away and staring at the lamp, you would take on 123 millijoules in 8 hours.
Okay.
That's far less than the 479 of the current threshold limit value by a factor of 4.
Right.
So
Okay,
we've
so-
always said, and we've said this before, stay at least 7 feet away and you're fine for 8 hours or as long as you want.
Okay. So yeah, if I'm 10 feet away and I've only got in 8 hours, I've only got a quarter of the safe exposure level, which is conservative. You know, if I even sit under it 16 hours, then I've got, you know, half of it. I'm still probably pretty good. So let's not, you know, hold the light right on our nose for, you know, 24 hours, but
Sure. In 24 hours, you're at 371 millijoules.
so basically, Moon, you can sit under your light all day. Just try to sit about 7 feet away from it.
Now, what I'd recommend though is that one of the interesting things about far UV is that you want to protect your plants because the photon energy is absorbed by the leaves of the plants, and that acts like a hot pellet. And so if you keep letting those photons hit the green leaf, it's going to basically act like a hot air gun, if you will, blowing hot air on your leaf. You're going to cause them to wither and turn black. So we want to have everybody recognize that far UV is fine for humans, but for many plants, it's not good to have long-term exposure.
Make sure they're at least 10 feet away.
Okay. How big of a room could you cover with 2 sabers if you had 2 on each side of the room, like perpendicular, I'm assuming, and you're trying to accommodate shadows for all the pathogens? So if you have perpendicular sabers, sort of what's the maximum size of a room that you would feel happy that is covered, assuming that you've got perpendicular sabers without shadows? Obviously, we know if we're putting stuff in between the light and wherever it's going, assuming there's no obstruction of the light, how big of a room can you get with 2 perpendicular sabers?
We'll figure that out, but each saber has about 160-degree view, as opposed to these Japanese that only have 40 degrees, 160 degrees versus 40 degrees. So this saber literally in a corner is going to cover the entire room. Now, the only difference is if I'm sitting between the light and Ed, he's not covered.
Right.
The lamp over on the side is going to get both of us.
Right.
And we have, I could pan up if I had the mic, but we've got a luminaire in the ceiling, and that covers down. Mm-hmm. So it covers everybody. So the reason we have the saber or the sconce so high is it's coming down and decreases that shadow area.
But Kara, the numbers that I calculate show that if you have an 8-foot ceiling, which means your walls are only 8 feet, that you can do about a 50 to 70 foot square room with 2 units and you're good.
Okay. 50 to 70 square. That's pretty good.
Yep.
All right.
But most people really don't need 2 units if they're only having, you know, the only reason for 2 units is when you have a lot of people in the room.
Well, sittings too.
Sitting, right.
Yeah.
If you got 6 or 7 people and you can reasonably distance them and everybody can see the light.
And they're moving.
And they're moving around. Absolutely.
Here's a question that I got. So my dad just told me someone called him, he thinks from Sterile Ray, and asked if he wants a $400 device. I was really confused. They knew he already bought the Saber, but that sounds to me like the X1. Does Sterile Ray have a small unit too?
No, and that was not Sterile Ray who called him.
Okay, that's what I thought. I thought that was really strange, and how they would know that he bought the Saber as well is also strange. So we may have to talk about that afterward.
Well, he probably talked with people, and they talk with people, and they talk with people, etc.
or post it on social media.
Yeah.
Yeah, and then the 160 degrees, yes, is that up and down and left to right?
Yes.
Yes. Okay,
Remember, the lamp is 10 inches.
right.
Well, I can, if I have that at the ceiling, I mean, I have the luminaire in the ceiling. I can get up to within a foot of the ceiling and still see part of that lamp.
Great.
So you can do it yourself. You can put it in the room, and as long as you can see the blue glow, you're getting photons.
Like I said, I can actually take the dosimeter cards and get photons. And I didn't do the complete blackness, but I got way far out, and I can still detect you on the dosimeter cards. So,
Gary, did you understand my write-up on the dosimeter and why that's not appropriate for trying to determine the efficiency at distance?
I don't think I got your right up completely. Maybe
I sent it. I don't know why you didn't get it. I'm sorry. I didn't.
that's okay.
Feedback. But the point of the dosimeter is that's a chemical thing, so it's not a photon counter.
Oh yeah, no. I got a Quantidose card. It's not a dosimeter. I have a Quantidose card that just detects whenever the light hits it.
Yep.
Yeah, and it actually, once I turned off the lights in my room, the biggest room that I had, I believe was only like 25 feet long, and I was able to get all the way to 25 feet long and still have a glowing card. And then if I turn the card to a shadow either way, of course, the card doesn't glow. So I could tell, like, I mean, all I was trying to do was see, would the photons be hitting it that far away? You know, like you said, the sort of, am I getting the paint splatter? And I was able to go as far as I could in the biggest room that I had and still get paint splatter on my card. So
yeah, my point of the matter is that you're asking for a chemical reaction, and generally speaking, the quantum efficiency is not 1 for 1. It doesn't take one photon to make a light that you can see.
Yeah.
So it could be 10%, and the sensitivity is really dependent on the chemical and the way they code it. There are a lot of factors on which card is more efficient than the other.
Right, so it could be less effective, but at least I know in the biggest, longest distance in my house, it may be more effective than that, but at least I know from that card that it is effective at least that far, according to my card. And my card may be spending 10% of the energy to make the reaction happen, but it's still happening, even with that expenditure at 25 or 30 feet, whatever it was that I was walking in that biggest room. I have a longer dark hallway in my clinic, and I still mean to go and actually have a sconce up, right? And so I still mean to go see how many feet down that hallway I can get, because I need it to be dark, because other light interferes and you can't always tell when the card's glowing or not, but it's really, you can see it really, really easily in the dark. So I want to go down that really long hallway I have and see what the distance is I can have my card light up. But I was actually really pleased, and the people that I showed were really pleased when I could show them how far away we could go and still get the card to light up. So
I think for most people in their living room or houses, you don't have 1,000 feet, so you're good.
Yeah, Kara, what's interesting is the sodium salicylate whitener that they put on copy paper. That's a very good photon converter. It picks up the UV and makes blue light. So compare your dot or compare your sample with just plain copy paper and see what you think.
I will. That's a great idea. I'll do that. I'm sort of an experiential person, so I will definitely try that.
Okay.
All right. Can I use it for a doctor or dentist office visit? We've talked about that before, and yes, you can use them for a doctor or dentist visit. But then they're actually asking how they would best place that in the small exam room, and adding to it, what's the coverage when it's laying on a counter versus on the stand? So can you just talk a little bit about, if you're going to the doctor or the dentist, where would you best put that light?
I took my Saber to the dentist every time I go with a DC adapter, so I don't have to worry about asking when to plug it in. And I just put it up on the sill, and I was probably 5 or 6 feet away from it. The coverage is great because I'm pointing it right at me. They always make me wear glasses, and obviously I'm reclined, so I'm not staring at it. But it worked great. And the dentist, the hygienist that cleaned my teeth was more curious. No one asked me to turn it off or even asked me what it was until I was in the chair and turned it on.
And
So-
what's important is that if you have a illuminated area in front of a patient, then you're guaranteed that nothing is going to survive that trip because it's getting hit a million times a second or more. And so that's a smart move to have it so that you're basically separating the patient exhale from the staff people that work there. So that's what you want to do, is to make sure that you're not blinding or shadowing the area where air could get to the staff person if you're trying to protect the staff person from an infected patient.
So when we talk about using air filters, we say put the air filters closest to the source of contamination. That's our general rule. So if you have a repair person in your house, put the air filter closest to the source of contamination. Would the same thing be true with the SterilRay? Like if you're going to the dentist and the source of your contamination is the dentist, are we more concerned making sure that the light is hitting her exhalate, or that, instead of you, are you more concerned with keeping yourself out of the shadow?
I'm more interested in protecting what I'm breathing in, because the previous patient could have been breathing 1,000 viral particles with each breath.
True.
And the aerosolized could be sitting there floating. Before I walk into that room, it could be filled with COVID virus, not from the hygienist, but from the previous patients.
Good point. Good
So
point.
I want it on me.
Okay. Good point. Good point. All right. I have we have a few more minutes, and I actually have a question that I am obligated to ask you by my daughter. Okay. Now, I'm not sure that I'm going to like the answer, but I promised her that when Ed came on, I would ask her. Okay. And John, I think you may have heard this before, but I have a 22-year-old, and she's a musical performer. And up until this point in the pandemic, she performs outdoors in an N95, and she has a SterilRay that she places about 7 feet away from her, and it's sort of bubbling her outdoors. And now she's started to do some indoor shows. But when she does the indoor shows, she wears a PAPR, like the VersaFlow space helmet looking. She actually has a little NASA costume that she puts on, and her band has little alien goggle things they wear, and they have like a whole set theme around the fact that she's in a PAPR. But she would really love to take that SterilRay and put it, 7 feet from her in a crowded, smoky bar and perform. Now, if that were your daughter, would you put her in a crowded, smoky bar with the SterilRay on her about 7 feet away in an N95 mask, or without an N95 mask? Or would you encourage her to still keep her PAPR performance?
Well, as long as she's singing,
Yep.
as long as she's protecting herself and puts it back on as soon as she's done singing, before she walks off the stage.
I saw Ed shake his head no.
Here, let me give you some technical stuff.
Mm-hmm.
Number one, we know for a fact, and we've got proof of this, even from a big chocolate manufacturer, that far UV breaks down proteins. And proteins are the major constituent of any allergens. So if she has an allergy, then the far UV light is going to break those allergens down so they don't cause histamine formation in her body. So it will not affect her as pollen normally does. The problem is, though, I don't know
that she's immunocompromised, not.
Yeah, okay. But what I don't know is what it does to the tobacco and to the smoke.
Ah, good point.
And so I would say I wouldn't put her in that environment without a mask and a filter. But
Okay.
if it's not smoky, then I think there's probably a 96% chance that she's not going to have.
No, you just answered the question. The bars in Princeton are smoky.
you
So Papa it is. Okay. That's a good answer. I didn't even consider the difference between the clean air versus the smoke and the pollen. So, okay.
Yeah, we just don't know what it's doing. I do know for a fact that there are a lot of chemicals in the exhale from tobacco, and I just don't know what the absorption cross sections are for all those different chemicals. And some chemicals can be cancerous, but you'd have long absorption coefficients, so you'd have to have a mile of this chemical before far UV could do anything. So, you just don't want to take a chance if you're trying to breathe, or you could breathing secondhand smoke. I think that's a real serious problem.
Yeah, and there can be heavy metals, I think, in some of the smoke, or there can be metal. And you just said that the metal will absorb a lot too. So that's actually a really good point. See, I'm glad I asked the question.
It's going to shadow the virus too.
Yeah. All right, here's another one. If I'm staying in an Airbnb, will I be protected if I sweep the space with the saber, assuming that no one else enters the space? So if I'm going into an unoccupied space and I sweep it with my saber before I take my mask off or do anything else, can I assume that, the space is now safe? I've disinfected the air.
What I do is I take the saber out of my suitcase, I plug it in, I turn it on, and I disinfect the high touch surfaces, the things I'm going to touch. Because I've done swabs at multiple hotels over the last 15 years, and you do not want to sit on the couches, you do not want to touch the phone, you do not want to make a cup of coffee. But in doing so, if you leave the saber on, you're disinfecting the air in that room constantly as you're moving around. So I do the high touch surfaces, then I set it up on an area and run it for at least 5 or 10 minutes while I'm unpacking and stuff.
Yeah, Kara, I went even further than that. I stayed in a hotel recently that had an air vent that was close to the ceiling, and it was constantly blowing in air. Well, I don't know what room that's coming from.
Yep.
So when I came in, I turned it on, I pointed it at the air duct. When I went to sleep, I left it on pointing at the air duct. And I didn't get a flu, I didn't get a cold, I didn't get anything when I was there.
So I have a question relating with that. So I have an Apollo UVC, I don't know if you've seen it or not, but they're little personal UVC things, and they come with a remote control. So you can put them in a room, and it has like a 15-minute timer, or 20, or 30, whatever. And it comes a little guide. It tells you like how long it needs to be in what size space to do the disinfecting. And because the 222 light my skin can touch, I've always sort of thought of that Apollo as like a stronger disinfecting version. So when I've gone to like an Airbnb and stayed there, I've thrown my Apollo in the room for whatever the indicated time to disinfect it and the size. And then, I've actually not traveled with my saber yet, but if I did, I would probably, maybe set my saber up if I were, having other people come over or something like that, which I don't do also without testing, but anyway, I'm digressing. I'm just saying that for our audience. You guys know me. I'm very COVID cautious. But when I'm looking at your charts, one of the thoughts that occurred to me is that the 222 may actually be better at killing the virus than the UVC that I can't put my skin on. Is that what that graph was showing when you were showing like the DNA and what wavelengths will destroy it and stuff? Absolutely. The 222, I would be better off doing what Kathleen is suggesting, and sweeping the space with the saber and using the saber for a certain amount of time than I would even for my little Apollo unit. Is that right?
That's correct. The amino acids do not have a strong chromophore as much as the proteins. The virus, COVID particularly, is surrounded by a protein membrane, and that's what we target is the protein. So we get the RNA very, very quickly in a viral particle. We break the proteins in the bacteria, whether they're the different types. So you can go from one type, the negative, to the positive type of bacteria, and we break down all those proteins in the membrane. So I don't want to get too technical because people's eyes will glaze over, but But the concept is that proteins have the highest chromophore, which means it's most efficient at breaking down bacteria and viruses compared to 254.
So let me ask you, when you put that in, do you leave the room?
Of
You leave,
course.
you leave the apartment?
Yes. Well, I mean, so usually when I have an Airbnb, it's multiple rooms. So the first room I always start with, which is also the smallest, so it usually only takes a smaller amount of time, is I stick it in the bathroom, right? And then I turn it. I mean, it has a little remote control. It has a delay switch too. So and it has a motion sensor. So if you go in the room when it's on, it will click off. So it basically gives you like, I don't know, 10 or 15 seconds to get out of the room. And then it runs for however long the timer is that you've set it. So what I usually do is I go into the Airbnb. You guys can hear my Airbnb process. I go into the Airbnb. The first thing I do is open up all the windows and I throw that little Apollo in the bathroom and I haul my air filters in and I start my air filters running because I'm going to keep them continually running. Like I said, I hadn't had the Sabre long enough to have stayed in an Airbnb because we only do it like once a year or twice a year when we do that. And so then what happens is once the bathroom is UVC disinfected, then I'll take it and I'll move it to like the living room area or the bedroom or whatever, and I just go room by room. And yes, I leave the room. So it takes it like if we got to an Airbnb, say at 10 in the morning, it would take several hours to get the whole thing disinfected, and so we sort of
Wasting several hours of your vacation.
yeah, pretty much. But we would
do everything you've just done in probably less than 5 or 10 minutes.
Right. That's what it just occurred to me that I've been using this little Apollo unit when a Sabre can do it a lot more efficiently. So
Yeah, look at the slide I just put up, Kara. You can see that the single pass 222 got 100%, and the
99.
UVC 254 nanometer
Right.
got maybe 10%.
yeah, that one and the other graph that you showed about the efficacy for the DNA, that really made me think, oh, I'm using the wrong thing now. Or at least I would be if I were traveling and doing that.
The other thing, Kara, is you're not disinfecting the high touch surfaces in the bathroom because that thing is so far away. You would have to sit there for 10, 20 minutes, if not more. Whereas
it sits in the bathroom for 15 to 30 minutes, depending on the size of the bathroom. And then because I'm extra, I go in with the Clorox wipe and some like bleach. so I'm getting the high touch surfaces, I promise.
There you go.
Kara, let me give you some insight. If you walk into a bathroom with the wand and turn it on, you're going to see how well they clean, because those cleaning solutions fluoresce. So if they just do a cursory spray on the wall or the toilet or the mirror or the sink, you're going to see the spots that they missed because it's not going to glow. It really is fascinating.
I will send you some pictures.
And I had a kidney stone, and John came in with I was in the hospital, and John came in with a wand, and it was a shock to see how bad the bathroom was in that hospital.
Oh, it wouldn't shock me. I'm in healthcare. They're nasty.
Yeah, and what's interesting is that 222 brings it all out where 254 doesn't.
Mm-hmm. So yeah, we did have another question that says approximate time to leave the Sabre on in each room when you're going into a space that's not yours before it would be safe to unmask. So I think you just sort of answered that too. When you go into your hotel room, you turn your Sabre on, then you give it 5 or 10 minutes, you said.
That's only because of the air coming in from another room.
Right.
So, I never turn on the air conditioning if it's in a room. I only use it when there's, the single room air conditioners. So you want to try to block off air coming from other rooms. That's how the Princess Diamond, everybody got sick on the Princess Diamond, because on a cruise ship, that air goes from one cabin to the next cabin to the next.
Yeah, I think Joey Fox has a great, he has a great little, if you're going to stay in a hotel room, these are the steps you take. And this is how, he explains how the air comes in from the hallway under the door to, actually cause the air exchange and the ventilation. And he tells you sort of the steps that you can take to try to minimize the amount of shared air you have in a hotel room. In most of our groups, we don't have a whole lot of people that are staying in hotels. We have occasionally someone that might stay in a hotel, or even more specifically a motel, that so that you have those little just single air, window units or something like that. But most of our people, when they travel, would probably choose an Airbnb that has a step, but just so that they don't share air, so that there's not, the danger of having that extra air from somewhere else that you don't know coming in.
Exactly.
Worry about.
Pierre, what I recommend and what I do is when I go into it, if I go into a room at a hotel or something, and I have a saber with me, we lost her.
No, you're here. I just took you off a share because I can see you better.
Oh, okay. Well, that's cool. I go in, I just hold the lamp close to my face so that I know if I'm breathing any air in that room, it's going through the light region. So I'm photo disinfecting everything before it gets to my head. And that's all I care about. And in 4 or 5 minutes after I go around the room, I've got all the high touch surfaces. I've got all the air. I'm fine after 4 or 5 minutes. But I just make it a point of just making a pass around the whole room, getting the bed, getting the table, getting the phone.
You never use the phone anymore.
Yeah.
Well, I'll tell you, mentioning phones, the way I've explained this to some people, the sterile ray technology, and I mean, you're really a visionary, Ed, to come up with this and come up with it so long ago, and then have it, be practically applicable in this pandemic. And it's really changing people's lives in our group. People who before haven't seen their families in several years, and they've been able to, feel like they can safely see their families. It's helping us with our kids and their homeschool experiences. It's helping everybody be able to reconnect to our communities and our societies, and we really, really are grateful to you for that. I have explained to people, though, it's a little bit like, my grandmother, who, if I went back into, say the 1930s or the 1940s and said, look, Grandma, here is a box. There's no wires on it. There's nothing. You just type a number in and you can talk to anyone anywhere in the world. And she would have looked at me like I had lost my marbles. And so I think it's as big of a leap understanding this light and how this light can clean for us and how this light can protect us, as it would have been for my grandma to understand the cell phone technology. Now, that doesn't make this magic, right? Like, now we're all used to this, and this doesn't seem like magic to us anymore because everybody's used to using it. And I think what's happened is you've been so far ahead of the curve that we really do feel like it's like Star Trek technology. It's like it's futuristic technology that we're able to apply to our everyday lives now. So it's really amazing and really, really fascinating work that you guys have done, and we appreciate all of your efforts in helping, and we really hope we can help spread the word. I want to see these in public transit. I want to see these in healthcare. I want to see these in all the public spaces. I want to be able to go back to the library, damn it. So, I want my kids to have story time. I want to be able to put these in the schools, and I want people to understand how the technology is safe and how it can be utilized. And we, not gonna lie, we've seen it. The people who are on this call know we've seen it in the groups. We have some, Elle says she calls it witchcraft sorcery. We have some people in the group, some physicians that are like, oh, it's not studied. We don't have long-term studies of far UV on skin. You may have these kinds of, you may have these side effects that we don't know about yet. And, to which my reply lately has been able to be, well, look, we've got the guy who's working on people's corneas, who's been able to remove tattoos from people's skin. I think we have probably one of the foremost experts advising us on this in terms of safety and efficacy for human tissues. And so thank you so much. We're all, big fans. We really appreciate you taking your time to come out here and share with us and answer our questions.
Very good. Thank you.
That's a great analogy, the phone. I'm going to steal it from you.
Feel free. I'm going to stop the recording.
In the 1870s,